Okay, welcome back everybody. So in the previous video, I already talked about widening, which allows us to reach a fixed point earlier in the analysis by basically getting quicker to larger values in the lattice itself. And we already discussed, though, that widening generally shoots over the target, so it tends to give us more approximate solutions than we would sometimes like. Luckily, there's a technique called narrowing, which actually allows us to improve on that again. So narrowing may improve the results of the widening by actually applying f again. So let us take a look at the following definition. So we have the regular fixed point, which is basically defined through our MFP solution. So we are applying repeatedly f to all the different values obtained for every single statement, where we initialize everything at the beginning with bottom. And then we have our widened fixed point, so to say, so fix omega, which is the same where, except for the one we have on the left-hand side, we're applying omega at every single iteration, like you see here, right? And like I also previously defined already. If you do that, then basically we have this guarantee that the original fixed point, it's definitely more precise or it's smaller than the fixed point omega that we defined that way. But what's interesting now is that if you apply f to this fixed point again, so that's this definition here, then this is guaranteed to be in the middle of between these two. Okay, so it can be, it doesn't have to be, but it can be more precise than this fixed point solution that we have here. And it's still guaranteed to be at least as approximative as this fixed point solution here, right? So it's a sound approximation still of the unwidened fixed point, and it can be more precise than the widened fixed point, okay? And you can actually apply this an arbitrary number of times. And this may actually diverge. So it means by applying f again, we do not necessarily have to guarantee that this ever terminates. So you could be doing this indefinitely. But the point is you can stop at any time because you're always guaranteed to be in between these two values. And in particular, you're still guaranteed to be larger than the regular MFP fixed point. So you can't do anything wrong. You will always still have a sound approximation. Also very likely you are going to be more precise than with the widened fixed point. So in that sense, you know, there's nothing really that you can break by doing that. Let's take a look at a visual representation again. So a widened computation, like I showed you earlier, it basically looks like this, right? So the widening in these red arrows, it brings us always closer to the top of the lattice. And now when we apply f again, the point is that this can bring us down in the lattice again, like you see here. And this is then called narrowing. Why does that work? Let me show you at least one example to convince you that it can work. We have already seen this example before, right? And if you remember, in the in the widened case, we had the situation that I'm showing you here. So for x, we were computing this interval from 7 to infinity because that's the only interval that we could possibly compute using these boundary values that we had defined. And for y, after 3 iterations, we would be obtaining this interval here from 0 to infinity. And we already saw that this is not optimal, right? Because actually what we would like to achieve is such a more precise solution here where we retain this information that x actually carries the constant value 8. And for y, the value is actually okay, right? Because that indeed can only be said to be within the interval of 0 to infinity. This is incremented indefinitely, right? So that's actually, it's a large, but nevertheless, it's a precise representation of what's happening. But this is the optimal value that we would like to obtain. And what's nice now is that if you apply narrowing, so if you apply the data flow functions for this program to this abstract widened value that we have here, then this value down here is what you actually obtain. Because if you take this as an abstract input and then process this loop here one more time, then by processing the loop, you will basically recover the information that x actually, independently of anything that has been defined for x before, after the iteration, it's definitely going to have the value 8, right? So that will be then the abstract value that you obtain after this one more iteration of the data flow functions. And now again, one can worry about, okay, is this actually correct? And if so, why is it correct? And we can take a little bit of a further look at this. So basically, we get this relationship here, right? So if we take the fixed point of omega that we have already computed, so this widened fixed point, apply f to it, and then widen that again, then we definitely have the guarantee that this is larger than only the inner expression here, basically. Okay. But this is the same as this expression here, right? So it's just another way of writing it. And this again is the fixed point fix omega, right? That's just defined the same way. And so we definitely have this guarantee that these two are in this relationship. And then by induction, we know that for all I, we actually have this relationship here as well. And so in every single iteration, this is at least as precise as this one here. Okay. Also, we have this relationship here. And therefore, we also have this relationship here that follows directly from this. And by monotonicity of f, then we also know that for all I, basically applying fi to fix omega will give us a larger value than this fixed point here. So that means this is always a sound approximation of the MFP fixed point. Okay, so you can therefore never get smaller than the MFP fixed point, and you're always still guaranteed to get a sound approximation. If this was too fast now, I encourage you to take another look in your own time at home. We can have some observations about this. So the simple notion of widening is maybe a bit naive if you think about what happens here algorithmically, because the widening, it really happens at every interval and at every node, right? So here I'm talking about widening again, not narrowing. So widening we define in such a way that you apply it immediately after applying every single data flow function. But actually there is no need to widen intervals that are not unstable, right? So we only want to widen intervals actually that are monotonically increasing from one iteration to the next. And so there's actually no need to widen if there are no cycles in the data flow, right? If you're not really, reiterating over the same value and increasing it in terms of height in your lattice from one iteration to the next. And therefore, we can define a more powerful widening that actually looks a little bit at the history of the values, or at least at the last the previous iteration that we have done, and applies the widening based on that. So here we are assuming that we have a widening function that doesn't take a single argument, but actually two arguments, so two lattice values, where one is the value from the previous iteration and one is the value from the current iteration. And based on that, then creates a widened value. And it has to be extensive in both arguments and satisfies the following properties. So for all such increasing chains, we have the property that the following sequence converges. So basically are choosing here Z0 as the first value. And then in every next iteration, we're computing the value as follows. So we're taking the previous value that has already been computed, and we are widening that with the value from the current iteration, and that then produces our next value, basically. Okay. And this has to stabilize after a finite number of steps. Okay. And now, next, we are replacing the basic fixed point solver by one that computes the following. So initially, we are initializing again with the bottom element. And then we are again doing the following here. So like I explained, we are taking the previous value. We are then applying the flow function to that previous value. And we are widening based on these two inputs. And I'll explain in a minute how that works. And then this new widened value, now looking at this history basically, right? So looking also at the previous iteration, that will then form our resulting value here. And you can prove that at some point this will stabilize, and then you have a fixed point for some k. And in particular, the fixed point that we compute here, that is supposed, well, it's defined to be an upper bound of the fixed point that we would normally compute. So how do you compute such a widening operation then? If we do this for the interval lattice in particular, then we want to extrapolate unstable bounds, and only those unstable bounds, right? So these cases where we have instability, to, again, this finite set of boundary values B, okay? And widening for the initial case where we have the bottom element, it's defined trivially. So basically the bottom element is ignored. So we always take the other value. And then if we have widening on two non-trivial interval values, then it's defined as follows. And here it's important that this is, it's not a symmetric expression, right? So it matters that this is, the left-hand side value is the value from the previous iteration that we computed, and the right-hand side value is the one that we basically compute for the current iteration. And then the following definition makes sense. So if A1 here from the previous iteration is smaller than A2 there, then we simply take this one. So we take that to be our next left-hand side value. And else we want, then else, if that's not the case, then we want to widen, okay? Because in this case, we then want to take a value from this element, from this set of boundary values B, that is actually at least it's the maximal value that is still smaller than A2, right? So because here we are talking about the left-hand side of the interval, so it's definitely meant to be smaller than A2, but it has to be one in the boundary values. And for the right-hand side, it's simply the inverse definition, so that follows directly. And yeah, you're defining this pointwise down to individual intervals. So for the small example program that we discussed, we get the same result as with simple widening plus narrowing. But now we actually even obtain it without using narrowing. That's just for this particular example program that I showed you. Now, talking a little bit more about widening again, I told you that typically widening is done in such a way that you choose the set B of boundary values by looking at the constant that are already part of the program. I just want to show you one example by McCarthy, which is sort of infamous. It's called McCarthy's 91 function, and it's meant to be a challenge for formal program verification. And that actually has some interesting properties where you see that this approach somewhat fails, because if you carefully look at what this function here actually returns, it has the following properties. So it returns the value 91 constantly for every input that is smaller or equals than 100, and it returns x minus 10 in every other case. And so even for the input 101, it actually returns 91, because 101 minus 10 just happens to be 91. And obviously it would be nice if we had an interval analysis that could figure this out, right? But if you now consider the value 91, well, it's written in the comment, but otherwise it's nowhere part of this program, right? So even if we had some way of determining this property and somehow conditionally expressing for which input values we would have an output value, in the range of 91 to 91, by using the boundary values from constants in the program, we would not be able to model it, right? So we would have boundary values 10 and 11 and 100, but not actually 91. And so because that is not a program, the intervals chosen that way would not be very useful here. So that's what I meant to say earlier when I said it's often sensible to choose these program constants as boundary values. It's a sensible heuristic, so to say, but it's still a heuristic, and there can be programs where that is not a sensible choice, and here you see one. Before we conclude, I want to show you just how far widening functions can range in their complexity. So you can think of probably the most generic simple widening function in the world, which takes some integer value x as an input, and it simply returns x itself when it's, so to say, small enough, right? So when you're saying it does not need to be widened, right? So we are still okay in terms of the value range that we want, and otherwise it's immediately jumping to top, right? So that would basically give you some precision for smaller x values, and as soon as you get out of this range, you get immediately to top. So essentially, through this widening, you obtain actually another very simple lattice, right? That is very constrained, has a very small finite height, depending on how small enough is actually defined. So that's maybe not a very useful widening function, but it's an extremely simple one. But you can also think of complex or difficult widening functions. So for instance, here we have the example of a regular language. So consider a program that is actually building a string using just some string concatenation, and it's starting with an A, so with the letter A, and then iteratively concatenating some number of B's to it. Okay, then in the first iteration we would have the string A, then after another iteration we would then also obtain the string AB, and so on and so on. And ideally we would like to widen this in such a way that we retain, that we gain this information, that we're not just talking about an arbitrary number of bees here, but really about, we're using a closed expression to denote this arbitrary number of bees. So we're using B star to denote any number of bees. Okay. So you need to define an analysis that finds out that the desired result has to be that regular expression here. That's not impossible. One can define such widenings, but it's very non-trivial, and also then making sure that the function is monotone so that you get all these soundness properties, that is not very trivial. Okay, that's all I had for this week. So we discussed the widening as a means to basically obtain faster termination in your fixed point iteration. We also talked about different kinds of widenings that allow you to do this more precisely than in other ways. And we also discussed narrowing as a way to regain some precision that otherwise might be lost due to widening. Thank you very much for your attention. In the next week, we will be slowly then talking about call graphs and how they can be used to actually model inter-procedural control flow, so that we can then, in the next step, define also inter-procedural program analysis that span more than a single procedure in your program. I'll see you then. Bye-bye.